Educational consult. I'm Matthias. I'm going to be taking you on electromagnetic induction, one of the important concepts of physics, 102. So electromagnetic induction, EMI. Electromagnetic induction is the production of an electric current whenever there's a relative motion between what? A conductor and a magnet. Conductor and a magnet. So what's a conductor? As we all know from normal basic background, a conductor is a material that allows mobile electrons to pass through it. So on other examples of conductors, we'll be talking on charge carriers. So what are the charge carriers of a conductor? Basically, there are two charge carriers of the conductor, which are holes and what? Electrons. So of course, holes are just like an empty charge carriers now. There's a vacancy. It's a vacuum, and it's positive, while the electrons are the holes, the negative. So, understanding these very concepts now, we are going to move into how can you detect the conductivity of a metal. Let's go there now. Another example of conductor. Under the example of conductor, we have metals. So metals, as you all know, they allow charge carriers to flow through them now. That's what we're taught in our secondary schools now. But in this very note, we are going to introduce another concept known as what? The bands. And under this band, there are basically two, which are what? The conduction band and the valence band. So, valency is an empty, it's a vacuum, I should know. Empty space, so it will take the positive while the conduction band will take the negative now. So now, if you want to classify magnets under the conductor based on this very concept, we have this diagram now. Take for instance, there's a diagram here, and I told you the conduction band is negative and the valence band is positive. So we have the conduction band, we have the valence band, the conduction band, and we have the valence band. So now in this very stuff, which one do you think? Okay, let's have these three diagrams on the board now. I have the conduction band, the valence band, the conduction band, the valence band. So the next diagram, I have the conduction band, the valence band, the conduction band and the valence band. So from this diagram now, which one do you think is a metal, it's a semi-metal, it's an insulator? The first one, right? Because the gap between the valence band and the conduction band, the gaps, they are interwoven. So this therefore makes this one now a metal. How about the second diagram on the board now? The valence band, the gap between the valence band and the conduction band, it has a very narrow gap. That's to say, it has a very narrow gap. There's tendency of a little migration of electrons through this very stuff like that. And I told you basically that the two charge carriers of the conductor are what? The holes and electron. So it has a very narrow gap here, and which makes it possible for the migration of electron. It actually comes from the conduction band to the negative, the valence band to the positive. So there is actually a movement of electrons in this very diagram now. So this one makes it what? A semiconductor. So in this very one now, the gap between the valence band and the conduction band, it has a very wide gap. This one is actually different from the second one because of the gap. So it has a very narrow gap. And this narrow gap is called what? The forbidden gap. So I told you let's come back to this semiconductor now. The semiconductor has another variance properties that is detectable. Honestly, I told you there's a narrow gap between, if you should check critically, there's a narrow gap between this very stuff here, this very one. It has a narrow gap. Sometimes they'll tell you it's not that visible. It's not that visible, but there is a narrow gap here. There's a gap here. A gap actually exists, but it's not that visible. So how is it that then possible? Since this valence band and this conduction band are not interwoven, how is it then possible that electrons now, electrons, that's the charge carriers, can actually flow through? And we'll find that soon. So now let's look at the semiconductor proper. So when you're talking about semiconductor, I told you the charge carriers of the conductors are what? Electrons and holes, right? Those are the charge carriers of a conductor. So in semiconductors now, which has a very narrow gap. So this one is they actually divided into two very types, which are what? The N type and what? The P type. The N type semiconductor actually have enough or more electrons than holes, while the P type has less electrons than holes. That's to say, it has more holes than electrons. So in this very category now, having known these very examples of a semiconductor, let's just go directly to the types of semiconductors now, which are basically two. We have the extrinsic semiconductor and the intrinsic semiconductor. Extrinsic semiconductors are semiconductors that has enough purity, impurity rather. It has more impurity, has more impurity content than each normal threshold frequency. So with the impurity, this guy, the intrinsic semiconductor make us understand that semiconductors normally which are blessed with a narrow band, you can actually make this narrow band, can actually make it a conductor. How do you make it a conductor? By introducing impurities through it. This extrinsic semiconductor make use of a concept called doping. So what do you understand by doping? Doping is a concept used in our everyday life. Honestly, some of us do practice this thing unknowingly, but we don't know. Like if you should go to any phone repair stuff now, those people that actually repairs phone now, if you go to get your phone for a repair, there are certain things they will do, and you may call it magic, honestly, if you are not really observant now. They will take a foil or a resin now, apply it to that very metals they are dealing with now, and all of a sudden your phone pops up. What do you think is actually responsible for that? Doping. So doping is another concept, very important concept used in the US. So it's the process of adding an impurity into a metal, semiconductor, any of the bits, anyone you may have now. The process of using an impurity to increase the conductivity of a conductor. So in this semiconductor now, we are going to add an impurity into a semiconductor in order to increase its conductivity. And we all know the examples of semiconductors now, from your arsenic, from your germanium, gallium, as the case may be. So arsenic is usually a pentavalent salt now. If you want to increase the conductivity of arsenic, what do? You introduce a pentavalent compound into that very structure now in order to increase the conductivity of an arsenic. Take for instance now germanium. you want to increase the conductivity of germanium, introduce what? A tetravalent compound into the very iodine, into the very concept to order to increase the conductivity of germanium. So now, having known this concept, let's move to intrinsic semiconductors now. Intrinsic semiconductors are semiconductors of great purity. Thus, they are extremely pure, that they are almost categorized as a metal because they are blessed with no impurity. An example of such, we have diodes now. I'm not going to really venture on that now, but of course you know that diodes are normally semiconductors. Semiconductors under intrinsic semiconductors, which are blessed with concepts that can actually change a conductor from. You can actually change a semiconductor. Thus, you can change from extrinsic to intrinsic. It purifies an extrinsic semiconductor. That's the function of diodes. And there are basically two. We have what? PNP diodes. And we have what? NPN diode. So PNP diodes are blessed with has more holes than electron, while NPN diodes has more electrons than holes. We're using this concept when discussing the two types of diode, basically two types of diode, which are what? A forward bias diode and a reverse bias diode. We'll venture into that proper soon. So let's move to the next important concept. I told you electromagnetic induction, the production of electric current, whenever there is a relative motion between what? A conductor and a magnet. So we finished discussing knowing what a conductor is. Having known what a conductor are, what conductors are, let's quickly venture into the next properties there, which is what? Magnet. Magnet. These are other concepts we learned in secondary school. Magnet. Whenever you hear magnets like this, what comes into your mind? Attraction, right? Correct. So you can't define magnet without saying a few words on attraction. So let's venture proper into magnet. So magnets and magnetic materials, they are actually synonymous to each other. Just as magnetic materials usually allows what? Attractions amongst or between themselves. So we will now go directly into the polarity of a magnet. This word polarity may look ambiguous, but it's actually what you know. You do refer to it as what? The dipoles of a magnet. Of course, you know. In conductor we have what? A valence band and a conduction band. And I told you the negative charge actually comes from what? A conduction band. Why the positive aspect from what? The valence band. But in this very concept is entirely different. Okay, this is our magnet, this is our north pole, and this is our south pole, right? So magnetic materials actually present themselves with these very dipoles. And again, polarity of a magnet what the dipoles can also be referred to as what? The dipoles of a magnet. And again, test for polarity of a magnet. Test for polarity of a magnet. Do you have any clue on that? Test for polarity? Of course, you may come up with different concepts on this different explanation on this very concept. So the test for polarity of a magnet is simply repulsion. That's when you actually take a magnet, suspend a magnet in the air, there's a tendency for it to actually revolve around. The Earth is actually a big magnet now, a giant magnet. They may even refer to it as a huge magnet, presented with what? Geographical North Pole and geographical South Pole. That's when you suspend a magnet in air, it's tend gradually to the north and south direction due to the huge, as you describe magnets as a huge, at the Earth as a huge magnet. So that's how magnetic material usually operate. So here is the diagram of a magnet. Sorry, my diagram, my drawings may not be as accurate as that in a textbook, but this was just a clue. I believe the message is actually sent. So these lines are actually referred to as what? Magnetic lines of force. These lines of force are what actually makes a magnet. So and they say, and we're told that the magnetic lines of force actually originate from where it enters through the South Pole and leaves through the North Pole. So magnetic fields are regions. Magnetic fields. They are regions of space around a magnet where the magnetic tendencies are felt. So these magnetic lines of force are actually components of what? A magnetic field. Because they are regions of space around the magnet, around this very axis, where the magnetic tendencies are felt. So now, and it's usually represented or identified using this very word, Tesla. Usually denoted using this letter T. And let's go to the magnetic flux. What do you understand by magnetic flux? Magnetic flux. Very simple. Magnetic flux actually measures the exact numbers of what? The magnetic lines of force passing through an area. It measures the actual number of magnetic lines of force passing through an area. Take for instance now, I noted something here in this magnetic field. It's represented using B, but this SI unit is Tesla, denoted using T. So now magnetic flux actually works synonymously with magnetic fields. I told you magnetic flux it's the measure of the numbers of magnetic lines of force passing through an area. And is noted, it's represented or identified with this formula BA, and it usually uses this symbol known as what? Phi. One of your Greek alphabet now, Phi. Exactly. So it's given as phi is equals to what? BA. And I told you the B is what? The magnetic field, right? Okay. And now let's make this B solve the formula now. B, it will now give you what? Phi over area, right? Correct. That's to say, the SI unit for magnetic flux is what? The Weber. Usually represented using WB, right? So now let's check, since magnetic flux is represented using Weber, so let's check for the magnetic this magnetic flux is represented using Weber. Let's check for the magnetic fields now. And magnetic field is given as what? Weber per meter. I told you the SI unit for magnetic field is what? Tesla. So let's have it as Weber is what? magnetic flux is represented using Weber, right? So our area, of course, area, meter squared, right? So now let's have it as, that's to say, if you want to pair the whole thing together, you have it as what? Weber meter per second, Weber meter squared. So that's the SI unit that's another name for magnetic field, Weber meter squared. Now let's move to the next important topic, known as what? Subtopic rather, known as what? The Lorentz force. The Lorentz force is usually used to represent the charge on a moving conductor, and usually represented using the formula that's to say, it's actually blessed with a charge, a velocity, a magnetic field, and of course an angle. There's an angle subtained between the magnetic field and the charge. This is another important concept for you to know. Since there's an angle upload, or there's an angle uploaded, so this angle will determine the direction of this very Lorentz force. Now, take for instance now, if the angles are parallel, and parallel angles, the angles usually 0, and our sine 0 is what? It will give you what? 0, which is equivalent to 180. That's to say, sine 180 will also give you 0. So an angle, if they asked you to find the magnitude of the force or magnitude of the Lorentz force when the angle subtruded is between the charge and the magnetic field is 0, that's to say the force attributed will be 0, because sine 0 is tantamount to 0, sine 180 is tantamount to 0. So take for instance now, if you are given a situation where they say the angles are perpendicular, so what comes to your mind? Perpendicular angles are what? Sine 90, right? So perpendicular angles are at 90. So we have it as sine 90, which is 1. And sine 90 is perpendicular to 1. So 1 times this whole concept will also give you 1. And that's the maximum force, which we have it as what? F max, right? Is equals to what? Pure VB. So that's it for Lorentz force. So now let's go to the next important subtopic again, which are force moving through a conductor. The force moving through a conductor. This is another important concept again. So let's take a look at this very diagram. These are the magnetic fields, right? I told you there are area or space around the magnet where the magnetic tendencies are felt, magnetic field, right? So these are the magnetic field, and the charge actually moves tangential to the magnetic field. And again, the length, if you want to measure the length of this very conductor, is synonymous with the conductor, right? So let's measure the length as this. The L, right? Why this one now is the current, the conductor, and this is the L, the length of the conductor now. So there's an angle uploaded here, which is what? Theta. So in finding this very force, you see the force moving through a conductor. We actually let's bring this up together. We'll see how F is equals to what? First one is B, right? The second one is what? I. The second one is L. As the magnetic field, the current, and the length. So the length obtained. Then the angle. There's an angle. Don't forget, there's an angle here. Now bring this sine theta. Just as we explained for Lorentz force, that this angle actually determines the direction of this very force. If the angle is in parallel, the angle obtained is in parallel, the force will now be 0, because sine 0 is what? 0, right? Sine 180 is 0. But if the angle obtained is angle 90, the force now will be maximum, which will now give you the maximum force, now be BIL, because sine 90 is tantamount to 1, and 1 times this very 1, you see about BIL. Okay. So now let's introduce another important concept known as what? The Biot-Savart law. Maybe on our next video we'll be talking about this very one proper, but I want to just use this very diagram to illustrate what a Biot-Savart force actually means. This Biot-Savart force is actually, it refers to the magnetic fields. I told you the length in the magnetic fields, the area of space around the magnet where the magnetic tendencies are felt by, right? So now it has a conductor now, the conductor which are measured using this very length, and there's an angle obtained which is L, right? So Biot-Savart law actually brings this ideology of measuring the total current flowing through a circuit, not total actually, just a substantial current of it now, half of it, and making use of what? The half of the length as well. This force moving through a conductor makes use of the whole length of the conductor of wire. But this Biot-Savart law makes use of half of this one. That's to say, if you are to circulate this very one, we'll have what? L1 probably, and L2. So that's Biot-Savart for you in relation to what? The magnetic field. So we have what? Our dB, which is proportional to what? dl. That's the length, change in length. I told you divide this length into 2 now, into 2, change in length, times what? The current obtained. And of course there's an angle obtained as well. You must take note of the angle as well. Take note of the angle. So now the distance between this very length and this very one, we need to take note of it, which are, you now what? Square the distance. So you know the laws of physics now. In order to remove the proportionality sign, what would you do? You need to introduce a constant now. And the constant we are going to introduce into this concept, which will eliminate these laws of proportionality, symbol of proportionality, is this very one. Change in B now. We'll now have it as U0 over what? 4 pi. This is the constant now, proportionality constant. This I, that's the current, dl, sine of the angle obtained over r squared. So if we want to write this one in relation to differentiation, if you want to write this one, express this stuff in a more elaborate form, we'll have it as what? U0 over 4 pi. Then we have what? Factorial I0 dl sine theta r squared. So that was it for Biot-Savart law. We'll talk about this, we'll elaborate on this more when on our next tutorial, because we'll be hitting magnetic field on the next tutorial. We'll explain all these things in details. Now let's go back to our normal concept of electromagnetic induction. This one are just the sub-branches now. I told you electromagnetic induction is the production of an electric current whenever there is a relative motion between what? A conductor and a magnet. For proper discussion of this very stuff, that's why we have to touch this conductor and magnet. So now let's go back to our electromagnetic induction now, proper. Let's go back to the laws of electromagnetic induction now. So the first law we have here is Faraday's law on EMI. So this Faraday, he actually came up with an experiment that made him to make this such propoundment of this very theory. He had an idea of a whole circuit. Take for instance, so Faraday's had an ideology of this the whole circuits like this. So he did this very experiment now. He puts a magnet into a wounded wire coil, just as we have it here. A wounded wire coil magnet. And this wounded wire coil is also called what? Solenoid. So he actually puts a magnet into this very wounded wire coil. He noticed that when he puts this very magnet in, there's a detection. This very galvanometer now, it measures the least current produced in a circuit. Galvanometer, it measures the least current produced in a circuit. So he noticed that when he puts this magnet into this very wounded wire solenoid now, wounded wire coil, he discovered that there was a detection, there was a movement in this very galvanometer. So he now said, so it is very possible. So he was on the concept that it's very possible to actually produce a current from a magnet. It was the first one that introduced this very concept. And let's take it slow now. It's not saying that whenever there's a relative motion, between a conductor and a magnet. I told you this wounded wire coil is also known as solenoid now. So it's a conductor and a magnet. Electromagnetic force is always induced. Whenever there's a relative motion between the conductor and the magnet, electromagnetic force, that's EMF, is always produced. So what do you know about this EMF now? EMF actually moves synonymously with potential difference. Of course, they have the same SI unit, volts, and all those stuff like that. And you know potential difference. The major difference between these very two are, let's have the diagram of a circuit here now. this is our voltmeter, because normally voltage, the voltmeter usually lies parallel to the circuit. Then our ammeter now. Then here is our key, and of course this is the source of the EMF. This is the source of the current rather. So the source of the current, just put it like that. That's the battery. So the difference between EMF and potential difference is that EMF, if you want to measure EMF, is when the key is actually opened. There's no current flowing through this very circuit. That's EMF for you. When you ask to calculate the EMF, that's to say the current, the whole stable, the whole arrangement here is static. There's no movement. There's no movement of current. But in the case of potential difference now, the key is actually clicked together. That's to say this one now is a complete circuit. There's a perfect flow of current now. So that's potential difference. Potential difference is used when the key is closed, while EMF is used when the key is open. Back into our concepts now. I said Faraday's laws of EMF say that when there's a electric motion between a conductor and a magnetic field now, electromagnetic force is induced. So now let's go to the next concept, the next law on this very stuff now. He actually, Faraday's law, and the next one is what? Lenz's law now. So Lenz is actually based on this experiment. Lenz actually produced his own law as well. You know, Faraday says, based on the movement, he actually denotes this very diagram now and said if you actually put a magnet into a wounded wire solenoid, the galvanometer, there will be a detection in the galvanometer showing that, indicating that there is a current, and that current is known as the induced current now. So Lenz now went ahead and said to detect the direction of this very current. So Lenz said if you actually put the thing this way now, if you put the magnet this way, the magnetic, the galvanometer will actually, if it's entering, the galvanometer will detect this way. If you are removing it, the galvanometer will detect this way. But if it remains static, the galvanometer will be at center zero. So now let's go ahead and set Lenz's law. Lenz's law states that the induced EMF, that's this whole place, induced current now. Induced EMF is in a complete circuit. EMF rather is in the open circuit, while the potential difference is a closed circuit, as we earlier discussed. So this Lenz's law said that the induced EMF always flows in such a way as to oppose the motion producing it. What this guy actually means is that when you put, just as I earlier explained, when you put a conductor through this very coil, the direction of this stuff will move in opposite direction as to the motion of this very magnet. So if you should put it this way now, it will detect this way. It will change directly to this way. So if you're trying to remove the magnet now, the galvanometer will detect. If you are putting the magnet, it will detect this way in opposite direction. If you are putting it, it will detect in opposite direction. If you are removing it, it will detect the opposite direction. But if it remains static now, it will detect the what? It will be static, no movement. So that's Lenz's law for you. So based on this concept, we are going to be talking on the examples of the electromagnetic induction. These examples of EMF now. This, I told you, is usually practiced in our daily life. This EMF. Before we go into the examples of electromagnetic induction, let's quickly look at this very concept known as what? A dynamo. So what do you understand by this very concept now? Dynamo. What are dynamo? Actually, these are stuffs you experience in your daily life, your everyday life. So dynamos are when discussing dynamo, there are two concepts you need to know: electric motor and a generator. So electric motor and generator now. So dynamo is an electrical device that converts what? Dynamo is an electrical device that converts mechanical energy into an electrical energy, and at the same way converts electrical energy into mechanical energy. Do you get that? It's an electrical device that converts mechanical energy into an electrical energy, and at the same way converts electrical energy into mechanical energy. So the dynamo that converts mechanical energy into electrical energy is called electric motor. And the dynamo also that converts electrical energy into mechanical energy is called a generator. So having known these concepts now, there's an important concept we need to talk about, known as what? The left-hand rule. And what? The right-hand rule. So left-hand rule are being used in discussing electric motor. While the right-hand rule are used in discussing generator. So now, what's the left-hand rule now? What do you understand by left-hand rule now? It's simple. You can actually do this with the tip of your fingers. So left-hand rule actually states that when the first two fingers, that's 1, 2, the first two fingers and the thumb are held exclusively or mutually, that's at right angle to each other now. The forefinger, that's the thumb actually pointing to where the direction of the motion or the force, and the index finger pointing to the direction of the field, then the middle finger now pointing to the direction of the induced current. So you can have it as like this. So that's for the right hand rule, because I'm actually using my right hand in setting this very stuff, so it automatically means it's the right hand rule. So for left hand, it's synonymous with the left hand, only that of course left and right are not the same thing. They actually use the left hand now in presenting this whole stuff. So why considering the left hand now? The left hand rule. When I told you left hand rule is actually used when you're talking about electric motor, right? Correct. And the right hand rule is used when you're talking about a generator, right? Correct. So the same way we have left hand rule, it has the same synonymously we have right hand rule. Only that the question you need to ask yourself, is it left or right? The same thing. So the examples of EMF now. One of the examples we have here is AC. That's what our alternating current, right? Okay, subsequently we'll discuss all this. The next one we have is what? A transformer. Hope you know the difference between AC and DC, right? Alternating current and direct current, right? Direct current, as the name implies, electricity actually moves direct. It moves with time, it flows with time. But for alternating current, it alternates with time, and it actually moves sinusoidally or periodically. It moves like a wave concept. Right, to go up, downwards, and that's sinusoidal movement, up and down. That's for your AC. Then transformer, as you all know, transformer is an electrical device that is used to change, of course, the EMF of a circuit. It used to change the EMF of a circuit. That's why in transformer we have step-up transformer and step-down transformer. Step-up actually increases the EMF of the circuit, while step-down actually reduces the EMF of the circuit. So on our next video, we are going to look at AC proper and all those concepts that are in AC. Like we have our resonance, we're talking about it. We have our inductance, our capacitance, and impedance, of course. We're talking about the voltage across a moving AC, alternating current, and other concepts as well. We'll be talking about threshold frequency, and of course the phase angle obtained. So this marks the end of our class. See you on our next tutorial.